Hello, differential equations. This is the simple harmonic motion problem. I posted it, called it a practice problem. A 10-pound mass stretches a spring 2 feet. So I'm going to go over some of this, a lot of details I asked that I don't want to go over. But first off, at the beginning, a 10-pound mass is not the mass. That's the mass times gravity is the 10-pound force. So you divide by 32, and 10/32 or 5/16 is the mass. And that 10-pound force stretched the spring 2 feet, so the K is 5. So that gives us this differential equation. The mass times x double prime, no beta, no damping constant yet, and there's K times x. And it's pretty simple to solve. I'm skipping that part. By the way, in the problem there was some initial conditions. It was pulled down half a foot below equilibrium, and down is positive, half a foot below equilibrium, and released with a downward velocity of 1 foot per second. That's the initial velocity. And when you solve this DE and use the initial conditions, here's the answer. Here is the answer. And then this is C1, this is C2, and you need to put it in alternative form. And the alternative form ended up being, let me see, it was this, I got it right here, I'm sorry. The square root, you ought to try to do this. My other video teaches you how to do this. The square root of 5 over 4 was the amplitude. I'll remind you, the amplitude was C1 squared plus C2 squared. And phi was the phase angle, and it was the tangent inverse of C1 over C2. So when I did that, I found phi. Now this is omega t. The 4t matches the 4t, plus here comes the phi. The phi was 1.107 radians. 1.107 radians. By the way, that C1 and C2 were both positive, so I was in quadrant 1. Whatever I warned you about, the calculator could mislead you, but this is exactly what we're angled in quadrant 1. So there we go. There's the alternative form. I asked you to graph it, which you could either graph that or that. They're the same. This is the alternative form of the position equation of this mass oscillating. It is simple harmonic motion, so it's going to oscillate forever. Here's my rough graph. What I do is I start at half a foot, because I remember that's where it started, at half a foot. It got pushed down, and that means it went down a little. That's down. I'm sorry. That's down a little. And then it comes back through equilibrium and oscillates forever. I asked you what the period was, and the period is always 2 pi divided by this omega, 4. This number 4 in front, the coefficient of t is omega. So there's the period, pi over 2. And what that is that's seconds. And by the way, we could just make it a decimal if we wanted. That's 1.57 seconds. What the period is it's the time it takes to do one oscillation. So on this graph, you can pick any. That's an oscillation. That's an oscillation. Back to that starting point. So the time for one oscillation is 1.57 seconds. The frequency is the reciprocal of the period. The frequency is, so it's 2 over pi. And so that is 0.64. And that's the reciprocal, so this was seconds per oscillation. This is oscillations per second. I think that's also known as hertz. But it's 0.64, that's the frequency. The reciprocal of the period. The extreme displacement from equilibrium, that's the way our book talks. That happens to be the amplitude, the extreme displacement from equilibrium. And it's slightly over a half. It got pushed up and it just was slightly over a half. It's this number. It's the square root of 5 over 4 feet. That is 0.56 feet, approximately 0.56 feet. So, cool, we're doing good. We're answering these questions. They're easy. This is a good question. F, what's the first time the mass passes through equilibrium? the first time. So I want to find out when it passes through equilibrium, you can set this equation equal to 0. Now I'm setting this equation equal to 0 rather than this. It'd be much easier to deal with this alternative form. You know, I set this equal to 0. I set x equal to 0. I can divide by that. That means I want to know when the sine equals 0. Well, the sine equals 0 when the angle is 0 or pi. By the way, that's the angle. So 4t plus 1.107 equals 0 or pi or negative pi or 2 pi or negative 2 pi. There's a lot of places where it passes through equilibrium, as you can tell. I am looking for that first time. I'm looking for that first positive time when it passes through equilibrium. Look at this. If I set it equal to 0, the angle 0, I would move this over and I'd get a negative number. My time would be negative. So I'm looking for the first positive time. It's not going to be that one. It's going to be pi. If I set it equal to pi and move subtract the 1.107, divide by 4, I get my answer. I'm looking for the first positive time. It could be any of these, but it's not 0. It's not that. It's not 2. It's the first positive time, and that happens at pi in this example. So we get this answer, 0.51 seconds. You could verify that with a graphing calculator. If this was graphed, you could look for that first t-intercept there. You know, they want the velocity at this instant. The velocity is the derivative of the position, and we can do that. The derivative is x prime. The derivative of sine is cosine. You know, the chain rule is going to spit out a 4. That 4 is going to cancel with that 4, so I'm going to do a little of this in my head. I get the square root of 5 cosine of 4t plus 1.107. Now, this is the velocity at any instant. It's called the instantaneous velocity, or the velocity at any instant. Not to be confused with the initial velocity, which just was that initial number. So the velocity at any moment, you know, I want the velocity at this moment, so I should plug in the 0.51 seconds. And I can do that and do the calculator and do some math, but I want to point out something. I just set this equal to pi to get this t value. So when I plug this t value back in here, the angle will be pi, and the cosine of pi is negative 1. So the answer is negative square root of 5 feet per second. That's the velocity at this instant, which again, we could decimalize that also, negative 2.24 feet per second. So that's a lot of good questions. A, B, C, D, E, F, G. And you should try it. Hopefully you can get those answers and work on that problem. I'll have some more. We need to work on damping. I got some more assignments coming up, more videos. Thanks for working hard. Thank you.